In this lesson, we will study one-sided limits and limits involving infinity. Now, it's important to note that so far we have discussed limits that are considered two-sided limits. The values of x get closer and closer and closer to some value a from both the right and the left sides of a. Here in this lesson, we're studying one-sided limits. We're going to study a right-hand limit and a left-hand limit. Okay, so the first one I'd like to show you is the right-hand limit, and it's written like this. The limit of the function f of x as x approaches a, now here it is, folks, with this plus sign right here, means as x approaches a from the right. That's what this means. From the right is equal to some real number L. Okay? Now, let's write a left-hand limit. Here we have the limit of a function f of x as x approaches a from the left is equal to some real number L. Now, it's important to note that the limits at a from the right or from the left are not affected whether the function is defined at a, okay? Also, the rules that we presented in an earlier lesson for evaluating limits also are valid for these one-sided limits. All right, let's look at an example. All right, we want to find each of these one-sided limits. These are one-sided limits for this piecewise defined function. Okay, so this is a piecewise defined function. There's three pieces. The first is linear, the second is constant, and the third is quadratic. So you're going to have a line, a diagonal line, a horizontal line, and then you'll have a piece of a parabola. And the first limit that we want to consider is the limit of this piecewise defined function as x approaches 2 from the right. And then we will look at your function values as x approaches 2 from the left. So let's first get a sketch of this graph. All right, here's the graph. This is the diagonal line. That is the first piece. It's x plus 6. Notice that it's only defined for x values that are strictly less than 2. There is an open circle here. This is the constant. So I did say that it was going to be a horizontal line, but you know what? This constant is only defined when x is equal to 2. That's the only location. So when x is 2, the y value is 5. And then we have this parabola, a piece of a parabola, and it's only defined for x values that are strictly greater than 2, which is the reason why there's an open circle here. All right, so what do we need to do? We need to evaluate each of these one-sided limits. Let's go for this right-hand limit, We have to consider what is happening to our function values as x approaches 2 from the right. So let me show you. My x values are approaching 2 from the right, and my function values are approaching what value? They're approaching 2, right? Now I know that at 2 the function is defined to be 5, but that's not what's in question. The question is, what are your function values doing, or how are they behaving, or what's happening to your function values as x approaches 2 from the right? So then the final answer here for this limit is 2. Okay, now we will consider what is happening to your function values as x approaches 2 from the left. So here I go, I'm approaching 2 from the left, and if I look at my graph is approaching, you got it, it's approaching 8. Now I know that when x finally arrives at 2, the function is 5, but that's not, again, it's not what we're considering. It's as x approaches 2 from the left, my function values are approaching 8. So the limit of that left-hand the left-hand limit is equal to 8. All right, very good. Now, I want you to note that, if you actually plug 2 in, f of 2 is equal to 5. And that is neither equal to the right-hand limit or the left-hand limit, right? F of 2 is equal to 5, and 5 is neither the right-hand limit nor the left-hand limit. Now, these one-sided limits exist. However, if I were to ask you what is the limit as x approaches 2, in other words, if I were to ask you for a two-sided limit, you would say it does not exist, because remember, in order for it to exist, for a two-sided limit, the function values have to be approaching the same real number value from both sides of 2. So the limit of this piecewise defined function as x approaches 2 does not exist, because from the left it's approaching 8 and from the right it's approaching 2, and we would need those values to agree to be the same value. So although the two-sided limit does not exist, this is how I write does not exist, the one-sided limits do exist. And you know what, as I'm speaking, I noticed that I forgot the argument here, so it's the limit of f of x. So please excuse, oh, that's really sloppy. Let me see if I can fix that. Just please squeeze in f of x here. That was poor notation. The limit of f of x. Okay, so make sure you put f of x on both of those. All right, cool. Let's look at a new example. Okay, we want to evaluate or find the one-sided limits for this given function. The given function is the basic square root function, and we want to find this right-hand limit and this left-hand limit. And it's for both of them, it's x approaches 0 from the right, and this one is x approaches 0 from the left. Let's get the graph going, and then we can evaluate our limits. Okay, here is our graph, and let's go for the first one here, the right-hand limit. X approaches 0 from the right. So here it is, x is approaching 0 from the right, and your function values are approaching 0. So the limit, the right-hand limit is equal to 0. Now let's consider the left-hand limit. So I'm allowing x to approach 0 from the left. The problem here is that the graph, the function, is not defined for x values that are less than 0. So the graph does not even exist over here. Therefore, the left-hand limit does not exist. Okay, cool. So now what I would like to discuss with you is how do we evaluate a limit that involves infinity? Now, consider the following function that is graphed here. As x values approach a from the left, that's what this says here. As x values approach a from the left, notice that your function values are growing arbitrarily large, right? So that it's going toward infinity, so we write infinity. The same thing happens on the right. Notice that as x values approach a from the right, that's what this says, the function values are growing arbitrarily large. So it's going toward infinity. So we write infinity. Now let's be very clear. The infinity symbol does not represent a real number. So although we say that the limit of this function as x approaches a from the right equals infinity, the function does not have a right-hand limit, because remember, the limit has to be a real numbered value, and infinity is not a real number. So we only use this symbol, infinity, just to express the way in which the limit does not exist. In addition, notice that because the left-hand limit and the right-hand limit agree, because they both are infinity, I'm going to say now that the two-sided limit, the limit as x approaches a, basically from both sides, is infinity. I thought it was very important to have the following in your notes. This was what I was speaking about earlier. Remember, a limit has to be a real number, and infinity is not a real number. But we're just using the symbol to show or to describe how it is that the limit does not exist. The right-hand limit does not exist. So this is describing to us, giving us an image or a picture in our minds as to how the function values are behaving as x approaches a from the right. Okay, now let's look at this function. We want to consider the left and the right hand limits. So what we're going to say is the limit of this function as x approaches a from the left is negative infinity, and the same is true for the limit of this function as x approaches a from the right. The function values are approaching negative infinity because the function values decrease. They decrease without bound. They decrease forever, right? Remember that negative infinity, like infinity, is not a real number. We're just using this symbol so that we can express how it is that these one-sided limits do not exist, right? The left-hand limit does not exist because it does not approach, the function values do not approach a real number. Same thing is true for the right. The right-hand limit does not exist because it does not approach a real number. However, we can describe what is happening to the function values by saying that the function values are decreasing without bound on both sides. And by the way, because they are decreasing, the function values that is, are decreasing without bound from both sides, because it's negative infinity on both sides, I can say that the limit of this function as x approaches a is negative infinity because both of these agree. They are in agreement on both sides of a. So therefore, the two-sided limit is going to be negative infinity. Check this one out. This is interesting. So let's consider the one-sided limits for this function. Notice that as x values approach a from the left, that's what this says, the function values increase without bound. So we say it's infinity. We describe that by using the infinity symbol. The limit as x approaches a from the right is we're gonna use the negative infinity symbol because the function values decrease without bound. Notice here that these one-sided limits are different. Therefore, we can say that the limit as x approaches a, right, from both sides, right, the two-sided limit for this function does not exist because they differ, right? From the left, it's one thing, but from the right, it's something else. All right, check out this graph. Another interesting graph. I invite you to find each of these one-sided limits here as x approaches a from the left, as x approaches a from the right, and then the two-sided limit as x approaches a. Why don't you go ahead and pause the video here, pause the lesson, and give this a shot on your own. All right, let's see how you did. As x values approach a from the left, that's what this says here, my function values are decreasing without bound. Therefore, I hope you said negative infinity. As x values approach a from the right, and that's what this says here, the function values are increasing without bound. So I hope you said positive infinity here. Now, that's a weird looking infinity symbol. Now, because these differ, right, because the function values are headed in different directions, we're going to say the two-sided limit does not exist. I hope you did well on that one. I'm sure you did. These are two popular functions that we've been looking at. This is the graph of the natural log function. This is the graph of the tangent function. I invite you to pause the lesson again and to evaluate each of these one-sided limits. This one is the limit as x approaches 0 from the right for the natural log function. One thing to keep in mind that for the natural log function, there is a vertical asymptote on the y-axis here, okay? Over here for the tangent function, consider the limit of tangent of x as x approaches negative pi over 2 from the right. Negative pi over 2 from the right. And the limit as x approaches positive pi over 2 from the left. Go ahead and pause the video and give these a shot. All right, let's see how you did. For the natural log function, as x approaches 0 from the right, my function values are decreasing without bound. So I hope you describe that by using the negative infinity symbol. For the tangent function, as x approaches negative pi over 2 from the right, as x approaches negative pi over 2 from the right, my function values are decreasing without bound. We can describe that by using negative infinity. And then as x approaches positive pi over 2 from the left, my function values are increasing without bound. So I'm going to use the symbol positive infinity. All right, good job. All right, let's try this example here. We want to find each of these one-sided limits for this given function. I invite you to pause the video here and use a graphical approach to evaluate or to find these one-sided limits if they exist. So go ahead and graph this function and then answer these two questions, okay? Go ahead and pause the video here and give this a shot. I hope this is the graph that you found. Notice that this is just the reciprocal, the basic reciprocal function moved 2 units to the right. All right, here we go. For the first limit, we want to investigate what is happening to your function values as x approaches 2 from the right. So as I allow my x values to approach 2 from the right, my function values are increasing without bound. So I'm going to describe that by using the infinity symbol. Whereas as x values approach 2 from the left, my function values are decreasing without bound. I'll describe that by using the negative infinity symbol. All right, very good. Now, I want to end this lesson by looking at limits as x approaches positive and negative infinity. Consider the following function. F of x is equal to 1 plus e to the power of x. So this is an exponential function, the natural exponential function that is just shifted up 1 unit. It does have a horizontal asymptote at y equal to 1. So the graph gets infinitely close to y equal to 1. It crosses the y-axis right here at 0, 2. Now what I would like for us to consider is the limit of this function, this natural exponential function. Watch this, as x approaches negative infinity. Here, please understand it the following way. As x values get smaller and smaller and smaller and decrease, what are your function values doing? So we have to read our graph this way. As x values, watch this folks, as x values get infinitely small, the function values are approaching what? The function values are getting closer and closer and closer and closer and closer to this horizontal asymptote, y equal to 1. So as x values decrease and get smaller and smaller and smaller, the as x values approach negative infinity is what I wanted to say. Your function values are decreasing and getting infinitely close to y equal to 1. So I'm going to say that this limit as x approaches negative infinity is equal to 1. Check out this example. It's pretty cool. Find each of these limits, the limit of the function as x approaches infinity and the limit of the function as x approaches negative infinity. So your x values are growing arbitrarily large, and then your x values will decrease, right, without bound. And here's the function we're talking about. It's f of x is equal to 5 plus 10 over 1 plus e raised to the power of negative 0.25x. Cool. Let's look at this first function. Now remember, or this first limit, excuse me. Remember, for this limit here, we're allowing x values to get infinitely large. Infinitely large. Now, what we must realize is as x values get infinitely large, this here gets infinitely small, this exponent here, right? And the reason that is because of this negative. So you got a negative 1/4 times this x value. So as this gets larger, you're going to multiply that by a negative. So imagine you plug in 100. Now this is negative 1/4 times 100, right? What is that? Negative 25. This becomes negative 25. And then it becomes negative 50, and then negative 100, negative 2,000. It just gets smaller and smaller and smaller. And remember, this is a negative exponent. So it becomes 1 over e raised to that power. So as x values get infinitely large, this term right here gets really small. It actually goes to 0. It almost becomes irrelevant, right? Because this is becoming 0. So then this whole expression is approaching the following: 1 plus 0. So then notice that this is equal to, if I can get my pen ready to type or to write here, this is equal to 15, because this is 5 plus 10, so it's equal to 15. So the limit is 15. Isn't that cool? And you know what? Let us use proper notation. So let's say, maybe I should write this like this. The limit as x values, and let me move up just a little bit here. Thanks. The limit as x values become arbitrarily large for this function is 15. There, a little more formal language there. There is the limit. Cool. All right, now let's think about as x values become really, really, really small, okay? Okay, so now let me erase what I've done here, if I can get rid of this. Okay. I trust you have all of that. All right, now let's go back to our function. Okay, now we already talked about this limit. Now, what happens to your function values? What's happening to this function as we allow x to get infinitely small? Now watch this. As x values decrease without bound, that means x values are becoming negative, and a negative times a negative is a positive. So this term here is becoming really large. And if this is becoming really large, when you add 1 to it, this entire denominator is becoming really large. And when in a fraction, in a ratio, when the numerator is fixed at a constant like 10, and then you allow your denominator to grow without bound, then this whole term, the whole ratio, is approaching 0. So then eventually this is happening. 5 plus 0, right? Because if this entire denominator is becoming really large and the numerator is fixed, then this whole ratio is turning into 0, is approaching 0. All right, let's use formal language here. The limit, I need to scroll up again. Okay, the limit as x values decrease without bound for this function is equal to 5. Weren't those a lot of fun? I like it because it got us thinking. All right, after doing this example, I think we're going to be able to derive a rule or after observing a pattern, okay? So what I want us to do is first look at the function 1 over x. This is the basic reciprocal function, and I want us to consider the limit as x approaches infinity and then as x approaches negative infinity. After we're done with that, I want us to look at this function 1 over x squared, and the same thing as the limit as x approaches infinity and the limit as x approaches negative infinity. Let's do 1 over x first. Let's get the graph right here and then evaluate these limits, and then we'll look at 1 over x squared. Here's the graph of that basic reciprocal function 1 over x. Now, as x values get arbitrarily large, not long, but large. As x values get arbitrarily large, and I can show that here, so as x values go in that direction, your function values are approaching 0. Remember that for the basic reciprocal function, the x-axis is a horizontal asymptote. And the same is true over here as x values decrease without bound, right? I'm doing this one now, folks. As x values decrease without bound, your function values are getting closer and closer and closer to that x-axis, meaning your function values are approaching 0. So I will say the limit of 1 over x as x approaches positive infinity is 0, and the limit of the reciprocal function, 1 over x, as x values approach negative infinity is also 0. Cool. Now let's look at the graph of 1 over x squared, or the function 1 over x squared. All right, here's the graph of 1 over x squared, and what I want to do is I want to consider x values approaching positive infinity. So as x values grow or increase without bound, your function values are again approaching the x-axis. In other words, your function values are approaching 0. Now, if I let my x values decrease without bound, notice that your function values are decreasing and approaching the x-axis again. So your function values are approaching 0. So I'm going to say that each of these limits is equal to 0. So I hope you see a pattern, and let's conclude what we have found now. So here it is, folks. The limit of 1 over x to the power of n as x approaches infinity is 0. And the limit of this same function as x approaches negative infinity is also 0. Here, n represents a positive integer. All right, one last example, and then we can conclude this lesson. Here we want to find the limit of a rational function. The limit as x approaches infinity of 5x squared minus 7x plus 1 over 2x squared plus x plus 5. So the technique that we're going to use here is we will divide both the numerator and the denominator by the greatest power of x that appears in the denominator. And the greatest power of x in the denominator is x squared. So you're going to see me divide every term by x squared. Why are we doing this? Well, because your x values are growing arbitrarily. They're getting larger and larger and larger. All right, so you've seen me divide each term by x squared. Let me move up here, okay? And so now this is the limit as x approaches infinity of, now what we need to realize is that we can use the quotient rule to say that this is going to be the limit of this numerator, which is 5 minus 7 over x plus 1 over x squared, right, over the limit as x values get arbitrarily large of 2 plus 1 over x plus 5 over x squared. We can continue using some of our rules here. For example, we can say this numerator is the limit as x approaches infinity of 5 minus 7 times the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 1 over x squared. This is just the numerator. Let me pause right there. We did use a constant, the sum, difference, and product rules here. So what we can do is this is going to be the limit of a constant. So we know what that's going to be, just 5. And we did use the product rule here to say that 7 over x is equivalent to 7 times 1 over x. And we know the limit of this constant is just 7, so that's why that's there. And the limit of 1 over x and the limit of 1 over x squared as x approaches infinity, we just talked about those, are going to be 0, right? We just stated that. Let's go for this denominator. So we have the limit as x approaches infinity. I may need to scroll up a little bit here. There. Of 2, and that's a constant, so that's just going to be 2, plus the limit as x approaches infinity. I think it's kind of funny how sloppy my word limit is becoming. Of 1 over x, and we know that's going to be 0, plus, and we can write this as 5 times the limit as x approaches infinity of 1 over x squared. Again, we're using a number of our rules here, like the constant rule, the sum and difference rules, and the product rules here that we talked about in earlier studies. Okay, folks, let's see what we have. So we have all of this is equal to 5 by the constant rule minus 7 times 0 plus 0 all over 2 plus 0 plus 5 times 0, right? So anyway, at the end of the day, it is equal to 5 halves. Isn't this really cool? I mean, what's really, really cool is if I can scroll up here for a second, and I don't mean to make you dizzy here, but 5 halves happens to be the ratio of the leading coefficients. Look at that. And I can make that huge shortcut as long as the degrees are the same. Isn't that great? Okay, folks, this is the end of this lesson. I hope you learned a lot. I hope you had fun. This is really, really interesting stuff here. So catch you later. Bye.